Okay, welcome to the fifth in our tutorial series on sequential Monte Carlo samplers. I am Dr. Peter Green, a senior lecturer at the University of Liverpool. And as usual, this video is made for the Distributed Algorithms Centre for Doctoral Training. As a very brief recap, where we got to in the previous video was that this was our estimation of a quantity of interest at iteration 2 of our sequential Monte Carlo sampler. We wrote down the sample variance of that estimate, and what we want to do is find the L-kernel, i.e. this distribution here, that minimises our sample variance. And in this video, we will finally derive an equation for the optimal L-kernel. So the first thing we're going to do to keep things simple is I'm going to take this whole expression here and I'm just going to write it as, let's call it g, noting that g is a function of x1i and x2i. That is just to keep the notation simple. So now if we move down here, what we want to do is, first of all, we want to write down an expression for our estimate at iteration 2 squared. Okay, so that'll be equal to, well, obviously we have a 1 over n at the front, so that is here. So we're going to end up with a 1 over n squared. Now what we have here is a summation of lots of terms, n terms. So for the next part, if we square that, then what we're going to end up with is a summation from I equals 1 to n, but also for a new index, j, from 1 to n, of g evaluated at x1 and x2i, and g evaluated at x1 and x2j. So we have to include all these, at least initially, all these terms where I is not equal to j. So we're going to calculate the expected value of our second estimate, or estimate at iteration 2 squared, and it's the expected value with respect to the proposal distribution, which in this case is expressed as this product here. And the key thing to note here is that samples I and j are independent if I is not equal to j. So that's what we've written here, is that the expected value of this g, we defined up here, expected value of g evaluated at sample I multiplied by g evaluated at sample j is equal to 0 if I is not equal to j. So that means that we can write our expected value of f2 squared is now just the summation of the expected value of g evaluated at sample I squared. So in other words, we're only considering the terms in this double summation where I is equal to j. So now we can write this is equal to still 1 over n squared, and the summation over our n samples. Now expected value is going to be an integral, and at this point we're going to substitute in our definition of g, which is here, and it's g squared. And as we said, it is the expectation with respect to this proposal. So we're going to write that proposal on the right hand side here. So q evaluated at x1i, and then our second proposal, or a proposal that gives us samples iteration 2. And we're going to write that this is over dx1i and dx2i. Now I've been a little bit lazy with the notation here. The thing to note at this point is that this integral will always be the same regardless of the sample. So essentially it's independent of I. So actually we can stop writing that this is the ith sample of x1, for example, and simplify things a bit, at least visually, by just writing that as a lowercase x1. So I'll do that now. And now we end up with essentially the same integral added together n times. So we know that we can get rid of this summation, and in fact it's just a 1 over n on the left hand side here. And so noting that we have a proposal squared on the denominator here multiplied by the proposal, then we end up with our target squared times L-kernel squared times the function we're interested in squared divided by the proposal. So now we have an expression for our expected value of our squared estimate at iteration 2. So now what we need to do is establish the L-kernel that will minimize this term. What we've actually got here is a constrained minimization problem, because what we want to do is find the L-kernel that will minimize our the variance of our estimate, essentially, but we have to make sure that the L-kernel is a valid probability distribution. So our optimization is subject to the following condition. We have to ensure that the integral of the L-kernel with respect to its argument, which is x1, is equal to 1. So our constraint, by saying that, our constraint is that the L-kernel is a valid probability distribution. The L-kernel is conditional on x2, so moreover we need to be sure that that condition holds for all possible values of x2. And we're going to do that, so the classic way of dealing with a constrained optimization problem is using a Lagrange, not sure, multiplier approach. So we won't specifically cover these in this video, so that might be something to look up if you're not familiar with, but it's a bit outside the topic of the current material. What we're going to do is we're going to first write down what we need to minimize using a Lagrange multiplier approach for the case where we consider a single x2, and then I'll generalize to the case where our constraint applies across all x2. So with the Lagrange multiplier approach, what we do is we say, well, the thing that we actually want to minimize now is, well, okay, first of all, it's what we wanted to minimize originally before we thought about the constraints. So it's the square of our estimate at iteration 2 minus a constant multiplied by the constraint that we've given, which we've got just in the equation above. That is the constraint that when integrated over x1, our L-kernel is equal to 1. And it's the constraint, so generally speaking, when we write our Lagrange multiplier problems, the constraint is phrased as some kind of condition is equal to 0. So to put it in that kind of framework, if you like, we can rewrite this to say, well, the condition is that that integral minus 1 is equal to 0. And that is now what we want to minimize when we've applied our constraint for a single value of x2. Now, if we had more than one value of x2, but a finite number, then what we've essentially got is multiple, but a finite number of constraints. What you would do in that case is here you would see a summation where we've got more than one constant here, more than one lambda, and it'd be a summation over the different possible values of x2 that we could have. Now it gets slightly more complicated in this case because actually, as we're thinking about a continuous case or situation, there's an infinite number of x2s that we can have. So that summation that we talked about then becomes an integral, and we have an infinite number of lambdas here as well. So what we're going to do is now, if we consider the case where we have continuous x2, then we're going to place an integral here, and it's going to be with respect to dx2. And what I'm going to do is just put in a dash here and here. So this is sometimes called a dummy variable, if you like, and it's just because when we expand our expression for the expected f2 squared here, then we'll have some x2s written here as well. So it's just to make sure that there's a clear difference between the x2s that belong in here and the x2s that are considered in this integral. And as we've also just said, it does mean that we also have, if you like, an infinite number of lambdas. So the best thing to do to represent that, or what we're going to do, is this is now, let's say, a function of our dummy variable for x2. So it's slightly more complicated than perhaps the standard form of Lagrange multipliers that you're used to seeing. The key thing is that we actually have an infinite number of constraints because we need to make sure that our L-kernel is a valid probability distribution for every value of x2, and x2 is continuous. So now we've got to this point. Now we've included our constraint for all values of x2. We need to find a derivative, functional derivative of this expression with respect to the L-kernel, set it equal to 0, and then we should get an expression for what the optimal L-kernel needs to be. Okay, so now I've just substituted in our value for the expected f2 squared from earlier. So that is all of this stuff. And now we're going to take the functional derivative of this whole expression in the square brackets, which is now very long, with respect to the L-kernel. And actually it's relatively simple, although it looks long and complicated. So if we deal with this stuff on the left-hand side first, what happens is this derivative will come inside the integral. We end up with a 2 multiplied by the L-kernel, after we've taken the derivative of the L-kernel squared. So we can put that term in first. Now if we look at this second term, what happens is we take the derivative with respect to this L-kernel, so it comes inside both of these integrals, and this integral comes out as being 0. So finally we end up with everything in this bracket has just been equal to -1, which gets multiplied by the -1 we see here. So now we can enter the second term. And now just to finish this off, if we say that we're going to set all of this stuff equal to 0, then it means that we're looking for the optimal L-kernel. So what I'm going to do is put a star here so that we note that L star is our optimal L-kernel as opposed to the generic L-kernel that we see here. So remembering that integrals can really be thought of as infinite summations, we can guarantee that this expression here is equal to 0 if we ensure that this expression below is equal to 0 for every single value of x1 and x2. So you can think of this as, in this particular case, we're only considering two specific values of x1 and x2, but we're going to guarantee that it holds for all of them, and by doing that we'll guarantee this condition above. Okay, now this is just a constant, so we can move it onto the right hand side of the equal sign, and we can also multiply it by other constants that we've got over here, i.e. this 2 divided by n. And so what we finally arrive at is that the condition we need to satisfy is that this term here is constant regardless of our choice for x1 and x2. So given that information, that implies that our optimal L-kernel argument x1 conditional on x2 is equal to, and I'm going to set it so this will essentially cancel to 1. So actually what I should really say, being thorough, is that this can be satisfied so long as the optimal L-kernel is proportional to, and we've got our proposal on the numerator, and then on the denominator, what we have here to cancel them is the target at x2 squared multiplied by f at x2 squared. And so by setting the L-kernel equal to this, and if you substitute it into here, then everything cancels and we've obeyed this relation. We know that this will always be equal to a constant regardless of the values of x1 and x2. So we finally do have an expression for the optimal L-kernel of our SMC sampler. Now there is a little bit of thought needed to consider what this equation actually means in terms of an implementation, but for now that is all the hard maths done. So as I'm sure you'll agree, it's a good time to stop the video, and then in the next video we'll focus more on how we interpret this with a few pictures, etc.